defined in the how to say, the static graph, computation graph. So the computation process is totally different. So the key of this course, this class, is to introduce you those core concepts of TensorFlow. And TensorFlow is evolving very fast. Google is releasing the TensorFlow 2.0 currently. So this time is quite an embarrassing timing to introduce TensorFlow, because after the 2.0, many of the functions, APIs in old TensorFlow will be deprecated. So the most important thing is to know the concept, not the very detail of each function call. The function call will change over time. Okay. Nowadays, there's many libraries: TensorFlow, MSNet, PyTorch, and CNTK. TensorFlow is released by Google, and this one is somewhat related to Amazon. PyTorch is developed by Facebook, and this is by Microsoft. As you can see, every major IT company has their own framework. But other than these libraries, TensorFlow is widely used by other companies, except Amazon, Facebook, and Microsoft. So if you are finding some internship in the IT company, most probably you will have to use TensorFlow. PyTorch is getting more and more popular in academia because it's very convenient and kind of beginner friendly. So in academia, people are doing researching and they are inventing something new. And the most important thing for them is to verify their thoughts as quickly as possible. They don't need the library to run very fast or to scale to a very large data set. TensorFlow does. TensorFlow is very scalable, and you can use it in the industrial level data set. I mean, industrial level means the number of samples like billions. So you need to use a whole clusters to compute the model. PyTorch, maybe you can run on your own computer, that's fine, but if you want to use PyTorch in the cluster, you will find some difficulty. So TensorFlow is released by Google in just 2015, pretty new. But as you know, the IT company is developing so fast, so TensorFlow has released 13 subversions, and basically each subversion is not compatible with previous one. So using TensorFlow is sometimes very annoying, and the users of TensorFlow complain a lot about these things. And why we provide this tutorial here? Because if you look for the tutorial online, you will find many tutorials, like tens of tutorials, if not hundreds. But one thing you cannot guarantee is what version of TensorFlow they are using. So if they use an old version of TensorFlow and then you are typing the function, you go, oh, I cannot find this function. Where is this function? You will get really confused. So we will introduce the whole framework of TensorFlow, and for each these the specific functions, you need to check their official website about how to use that specific function. We won't give some example of. We will only give example of simple function that won't change a lot. But for those complicated functions, you need to really check on their official website, because we don't know when they will change this function. Okay, and there's a very famous for deep learning with Python by, how to pronounce his name? Francois. This guy, he wrote the library of Keras, which is a library based on TensorFlow. And when you check on TensorFlow, their website, the first example they gives is written in keras. So keras is not a originally keras is a separated library from TensorFlow, but then Google hired this one, and they generally move keras into TensorFlow. And this book is mostly focused on keras. It's a very high level TensorFlow. High level means this one wraps some functions and they build some predefined models. Then when using keras, it's just like playing the Lego toys. Assemble some parts together, and then you get your model. And here's another very famous book, machine learning, Tensor machine learning, and something TensorFlow. This is the library we mentioned in the very beginning of this semester, right? We emphasize that you cannot use the function from this library. But after this course, or when you are doing your own project, I highly recommend you to use the function from this library. They are really well written, and their document is so excellent. You can basically know nothing about the library, just take on their document and use their function. And the TensorFlow part is somewhat outdated. They published in 2017, just like 1 or 2 years ago. It's already outdated, as we mentioned before. I highly recommend you to read the first 6 chapters of this book. They will tell you how to pre-process the data set and some really commonly used tricks on machine learning, which will greatly improve the performance of your model. Okay, and we will begin to introduce TensorFlow. I still want to talk about this one a little bit. If you are interested in deep learning, and you are not, you won't be finding a internship in industrial soon, I will recommend you to learn this thing first, because it's really beginner friendly and you can run your model really soon. Using this one, you need to learn some 1 or 2 weeks before actually getting something to run. It will be really frustrating. Okay, let's get started introducing TensorFlow. Why we need TensorFlow? First thing is the augmented tensor operation. We say tensor, we just mean the multi-dimensional array, just like in NumPy. This functionality is, I will say, identical to NumPy. Every one of you has been familiar with NumPy already, right? We use them so often in our course. When they develop TensorFlow, they intend to write their API that identical to NumPy, so people from NumPy can transfer to TensorFlow without any difficulty. And as you know, in NumPy there are so many implicit operations, like how to multiply two arrays highly efficiently. They will be the same in TensorFlow. And I will say the biggest functionality of TensorFlow is this one, automatic differentiation. Do you still remember the fear of dominated by calculating the gradient? In the very beginning of this class, the homework 0, we asked you to calculate the gradient of the logistic function, a very simple linear model. Have you remember how to calculate that gradient? It's hard, right? Can you imagine some very complicated nonlinear model, and you're asked to calculate the gradient by hand manually? So hard. But before these things, for TensorFlow or some other like NumPy, the PyTorch, these things, people are really manually calculating the gradients and code it into program. So in Cafe, a very old version of learning library. If you want to use a new layer, a new function, you need to calculate manually the gradient of that function in C++. So it is not popular now. People now use TensorFlow. And then another very big advantage of TensorFlow is it will get the parallel and distributed computation. Parallel means it will utilize your CPU and GPU. Nowadays, even for your own computer, we have more than one core, right? For clusters, they have like tens of cores, and for a big cloud, they have thousands and tens of thousands of cores. And TensorFlow can take care of the parallel and distributed computing for you. You just need to write your model, and if you run on different machines, your own machine or the supercomputer, the program you write will be the same, and TensorFlow will take care of these underlying things for you. So the code for the simplest model and the code for the most complicated model will be basically follow the same process. You don't need to worry that much about the computation part. So if your model is simple, you just run it on a small computer. If the model is big, run it on clusters. Okay, the automatic differentiation, which is through the back propagation, we just learned a previous course. I won't talk about this BP things anymore. You'll be asked to do BP in the homework 5, I think. But we don't need to know anything about this, because TensorFlow will take care of them for you. So basically, we need the differentiation. So every operation in TensorFlow you apply on the tensor should have some subgradient. If there is no gradient for the operation, then there's no differentiation. But maybe some of you may think this requirement is so strict, then we cannot use most of the operations you can think of. But actually, most of the operations on a tensor you can think of has subgradient. Like a mentioned function, plus, subtract, multiply, divide, or this mathematical function. Can you think of some operation that is not differential in this meaning? Is if statement differential?
Well, I was just going to ask, is division differentiable?
Why division not differentiable?
Because division by 0 isn't differentiable, and there's no subgradient for that.
Okay, if divided by 0, then they will rise a numerical error. Okay. Is if statement differentiable? If x greater than equals to 0, and then it takes a value, and if it's not, then take another value. It is differentiable. Just depends. Yes, it has such subgradient, just like max, right? We calculate max. Max is an if function. If it's greater than 0, then we take x. If it is not, then we take 0 or the absolute value. If it is greater than 0, we take x. If it is not, then we take minus x. So if statement is differential. Sampling is not differential. Say my parameter x is the probability, and I sample from this probability like 1 or 0, then we have no gradient here. But there's some workaround to approximate this operation. So basically, every operation you can think of is differentiable. So you can justify your loss function without any worry. Is my function differentiable or not? You don't need to worry about it. Okay. So working process, the framework of TensorFlow is easy just as its name. You divide the tensor, define the tensor, and then you let it flow. So what is a tensor? As we said, it's just a fancy name of the multi-dimensional array. The one-dimensional tensor is just a vector. What is a zero-dimension vector tensor? A scalar, right? If you print the shape of a scalar, it will give you an empty set. But if you print the shape of the 1D tensor, it will give you one number, two number, like this. So the 3D tensor, how about 4D tensor? You can think every element of this 4D tensor is a 3D tensor, right? Just like this is an image. We have pixels, column pixels, and row pixels, and different channel RGB. And I have a bunch of images, then we have a 4D tensor. Then float. Float refers to the computation graph. This is the core of TensorFlow and is the key different part of TensorFlow and PyTorch. In TensorFlow, you need to first define this computation graph and then execute this graph. It's not like NumPy. In NumPy, you define A equals 1, B equals 2, and C equals 1. Then you add them together. Immediately you get a 3, right? But in TensorFlow, if you write like this, C equal to A plus B, what you define is just an operation. You need to execute operation, then you get the result. So in TensorFlow, things happen in two phases. First, you define this computation graph. Second, you execute this graph. This is very subtle, but I will show you in the code. But when you write it in TensorFlow, you always have to remember this. When you define C equals to A plus B, something like this, you are just defining the operation, not the actual operation, not the actual value. If you think C here will have the value of 3, no, it doesn't have. It just has the operation. Until you execute this graph, then you can get the actual value of C. I will demonstrate these things in the code. You just need to have some concept of these two phrase execution. And TensorFlow has a library called TensorFlow. Then you can visualize the TensorFlow the computing graph you just defined. And for a very simple network model, you can visualize them. But if your model is really big, then it's sometimes really hard to visualize them. This is what we call this. As we introduced here, we need to predefine the computation graph and then execute. In TensorFlow 2.0, they are introducing this called eager mode. In this mode, you just operate the tensor like in NumPy. You divide two tensor and you call the add. You immediately get the result of the computation. So it's called eager. And in the static mode, sometimes we call it lazy evaluation. When you call the graph, then it will evaluate the value of the graph. If you don't call it, it won't evaluate. So in this course, we will focus on the static mode. And I think even in 2.0, Google is introduced the eager mode, but you can think of so many companies has already used the static graph in their product. So they won't change to eager as soon as Google won't. In a very long time of future, I think this one will still be the dominating, how should I say, the mode or the paradigm. So whenever we need to define the graph, there are many subtleties. I will show you in the code. And as we introduced, TensorFlow has 3 levels. In the very low level, there's a primitive TensorFlow, just like you are building your own vehicle by the smallest, tiny parts. But there's another library like Keras. It's a very high level TensorFlow. It's like you're building a car. You say, I want this engine, I want this tire, I want this window, and Keras will automatically assemble them together and give you a model. There's another thing called TensorFlow layers. It's somewhere between. This is just simply a wrapper of the primitive TensorFlow. It can save you some work to define the operation. I would say if you want to do something in machine learning, then you would like to use the primitive TensorFlow. If you are beginner to deep learning, you would like to use Keras. And if you are developing something new in deep learning, then you will like to use this one. Every new machine learning paper will contribute their algorithm to the TensorFlow layer. So if you find some paper, they propose a fancy idea, and then you would like to try the idea, maybe you can look here. You maybe find they already implement something in the TensorFlow. TensorFlow, they have a library called TensorFlow.contribute, which is someone outside Google contribute the algorithm to this TensorFlow library. They are not officially verified, or how to say. But if you want to use, you can use. But Google won't guarantee anything if you use the contribution version. Today I will introduce this one, and if we still have time, I will introduce something of this one. And I introduce this one so that you can use TensorFlow to do your machine learning work. And this one, if you are doing some deep learning in your final project, you can use Keras. It's very fast. In your final project, you are not supposed to propose something new or innovative. If you can just apply some neural network architecture to your data set and get some results and analyze those results, it will be a very good project. You are not supposed to, you are not required to propose something new. It's really difficult. Okay. Although they have 3 different levels of TensorFlow, but our working pipeline is the same. First, you define your input and the variable. Variable here specifically means the weights and the parameters. In our linear model, our input will be the data point, right? The data feature and their label. And the variable will be the weight and bias. If you are using Keras, you don't need to do this. You just say, I want this layer, I want this layer. Keras will take care of them for you. And then, of course, you need to define the computation graph from the input to the loss to the output. In the regression model, what will be the output? A single real value, right? In the classification, what will be the output? And depends on how many classes is in your task. Binary, then 0, 1, multi classes, and then you will output as many numbers as the classes of the classes. Then a very important thing is to choose a loss function. You have your output, and you also have your input label. Then how do you measure your model? And how do you know is this model good or not? You need to define the loss function. And usually we will optimize in terms of the loss function. Sometimes there's another term, say matrix. Matrix is something you use to evaluate your model. But when we do the optimization, we optimize our loss function. What do we mean by matrix and the loss function? Suppose we are doing the regression. Our model will give a real value as output, and we also have the label of input. We can use the L2 norm as loss function, right? But L2 is not so intuitive. If I take the square of the difference, it's sometimes hard for human to directly recognize what is the performance of the model. Then, for the matrix, for we to evaluate our function, we can use the L1 difference. We just take the difference and take the absolute value. Then we can directly see what is the distance, the difference. Okay, and then the final step will be to execute this graph. And Keras will also take care of the execution for you. They will automatically schedule the the input and the epoch, the batch size, and the shuffling of data, and all things like this. If we are using the primitive TensorFlow, then you need to shuffle the data and sample the batch point yourself. I will show this whole process in an example. So today we are going to demo the arithmetic operation and tensor operation in TensorFlow, and how to use it to build a primo SVM. Why not the dual SVM? Because in dual form of SVM, we are doing constraint optimization. Remember, we need to constrain the alpha in the specific range. In TensorFlow, you can have some workarounds to do constraint optimization, but normally in TensorFlow, we work on unconstrained problem, which is the primo form of SVM. Then I will show you a very simple neural network in Keras and in primitive TensorFlow on the digits classification. One big thing in TensorFlow is, in deep learning, is for a non-toy model, use the CPU to do the computation is way slower than you use GPU. So if you have some considerable size of data set and you want to use deep learning, you need one GPU. It will be too slow to train on CPU only. But unfortunately, TensorFlow currently only supports the GPU from NVIDIA. And how many of you know the difference between NVIDIA and AMD? No. Basically, if your laptop has a GPU and it has a green label, you have a green label like N something something, it will be a GPU from NVIDIA. Every laptop will have some label like Intel, NVIDIA, AMD. So if you only have AMD GPU, then you need to buy something else to do computation. Where to find the computing resource? First thing is your own gaming PC, if you have one. I use this one. And if you are familiar with the CHPC, Center of High Performance Computing in the university, you can use their machine, very powerful supercomputer. And if you are from College of Engineering, there's a K Lab down there, and they have, I believe they have NVIDIA GPU and a pretty good GPU. And if you are from some other college, you can buy the resource from your own department. And if you haven't used SW and Google Cloud Platform before, when you apply the account first time, they will give you a coupon like several hundred of dollars, and you can use the coupon to use their cloud computing resource. And if you have applied this before, then you can use Google Colab. They provide the free GPU and TPU, but so many people are using these things nowadays, so the speed of Google Colab is decreasing. Years ago, when I used the Colab, I get a full like V100. Now you can have the computation resource like 1/10 of V100. And if we are new to TensorFlow, I will recommend you to install TensorFlow is a Python library in our mini. If you are new to the TensorFlow, I will recommend you to install the TensorFlow through Anaconda. Anaconda is a software environment, and it will wrap the most commonly used software. And the good things of Anaconda is they will dealing with the conflicts of different libraries for you. And whenever the library is in their list, you can insert it without any conflict. Normally, if you install this library your own, you'll find some library require this version of other library, and some other require another version of the library. It's really annoying to deal with this conflict. But Anaconda will do these things for you. And Anaconda supports Windows, Mac, and Linux, pretty cross-platform. And basically every commonly used library, they have their version. So basically, this one is all you need, I would say, in machine learning. Okay, then we will show the actual code, how to use machine TensorFlow. How many of you bring your own laptop here? Okay, some of you don't. It doesn't matter. After all, you won't be able to catch up with me today, so I will be very quick. And besides, installing TensorFlow is really slow. It will cost you half the time of this course to install TensorFlow. So Anaconda is really easy. You should be able to install it. And after you install Anaconda, I will show in Windows. After you install Anaconda, then Anaconda will create a virtual command line console for you. This thing is different from the original console of your Windows. You can call the command in this console only provided by Anaconda. So I need to switch to the directory. So if you have any puzzles questions when I am typing the code, just ask me. I want you to understand every single line that I type here. You should be able to understand that. Nothing fancy here.
Did you make the text on the console bigger?
Just calling the. I am just opening the Jupyter notebook. You don't need to see something here. Jupyter. Can you see it from the back? No? How about this? Okay. I will upload this notebook if you want to have a look. And I think it's a very good introduction notebook. Okay, let's get started. First, of course, we need to import the TensorFlow. We also import NumPy and Keras, and this matplot library we use it to plot the image. And after we import the TensorFlow, we would like to check which version it is. Sometimes it's very important to check the version, because when you are asking, you are finding some bug or asking the question online, and if you have the different version of TensorFlow, then some bug in previous version won't be bug in the next version. And you need to check which device you are using. This one only has the CPU, so I don't have a GPU here, so I won't run some big data set here. Then we came to the first part, the simple operation.
Wait, real quick. So I thought you said. Oh wait, so you can just use the CPU exclusively?
Yes, we can. Yes, you just be slow. There's no requirement that you to use a GPU.
Okay.
So first thing that we want to do is simple calculation. A equals to 2, B equals 3, and C, A plus B, D, A multiply B, and C, and E, C subtract D. Very important, very simple, right? If we do this in NumPy, we just do something like this, A, B, C, D, E. And after this line of code, what will we get? What is the value of C? What is the value of E? This is 5, this is 6, and this will be -1, right? This is as expected. This is in NumPy. Now we do it in TensorFlow. As we said before, first we define the tensor. Scalar is also a tensor, right? The 0-dimensional tensor. And then we divide the computation graph. But the subtle thing is here. After we divide the E, after this line of code, what is E? It's just an operation. This operation takes 2 tensors, and this 2 tensor is also the result of the operation. So E here basically means this whole computation graph. So if we print those out, you see no value here. They are just operations. E here is just an operation of subtraction, right? And how do we get the actual value of E? Then the key part is here. We need to first define the section we call an execution engine of TensorFlow. And using this engine, we pass in a graph, and this engine will execute the graph for us and bring back the value. Here we get engine, and we pass in our graph. Then the actual value E will be computed by this graph, this engine. And now if we bring the evaluation, we will get actual value of -1. Very anti-intuition, right? You are doing calculation, but you don't get the result until you do the execute the graph. And one thing about the graph is it only executes the necessary part of the graph in order to evaluate this value. What does it mean? If we are defining a giant graph, but you only want to calculate one specific value of a single node, like this part here, and there's another giant graph, the engine won't execute this other part. It only executes those necessary nodes to get evaluation of the nodes that pass in here. But for example, if here we pass the D is divided by A multiplied by B, then the engine won't execute this node, because we don't need this node to calculate D. We only need to know the value of A and B, right? So when you're using TensorFlow, always keep in mind that you need to use a section to execute your graph. And everything you do here is just define the graph. And the parameter of this run call is a list of nodes that you want to evaluate. And you will return the evaluation of this node. Just as expected, 5, 6, and -1. Are we clear currently until now? This is very important for you to use TensorFlow. I would say this is key part of TensorFlow. The rule 1 is just you first define the graph and then execute. And for matrix computation, it will be basically the same as in NumPy. The only difference is we need to first define and then execute. So we define a matrix A and B, and what is this symbol here? As, what does it mean? Dot product. So we do this in Python, do this in NumPy. Everything goes as we expected. Then we do it in TensorFlow. Note here, if we would like to define a TensorFlow tensor, we can either pass a constant value to it, or we can pass a NumPy to it. If we pass a NumPy to it, then the initial value of this tensor will be the value of this NumPy variable. And this is a constant, so there's nothing like initial value. The value is just this NumPy. And then we do the dot product. As the same before, this C, T of C is just operation, and we need to execute want to change the value of this tensor, what you use? There's a thing called placeholder. I don't know why they came out with this name, but it turned out that this name is pretty suitable. The placeholder is just a place to hold the value. But when we define the placeholder, we don't know which value we will fit here. It's just a place. We know we will have something here, but we don't know what its value until we execute the graph. So if we don't know the value here when we execute the graph, which value will we use for this placeholder? Guess? You need to specify that in the phrase of execution. So as before, we define A and B as a placeholder, and we'll define them as a 2 by 2 matrix, like in previous case. And then we do the here we do the dot product. And this C will be the same as before. It's just a operation. It is the result of a dot product of two by 2 matrix where we don't know the value yet. Then we want to execute the graph, just like we executed before, right? If you run this line of code, we will write some error. Why? This is just placeholder. We need some value. Right? If you don't pass in the actual value to this placeholder, and the graph needs this value, it will write some error. The error will be a very, very long error because TensorFlow is writing in C++ and Python is just a wrapper, and a wrapper around it, level by level. It will trace down to the very deep level and write this error. But at the very end, you will see you must feed a value for the placeholder. If this node we want to active, we want to evaluate, doesn't need the placeholder, do we need to pass it? No. If TensorFlow is a lazy evaluation, if it doesn't need it, it won't evaluate. So if the nodes passed here do not involve with any placeholder, then you can just leave it. You don't need to pass anything to the placeholder. So the correct calling is like this. We want to evaluate this node, C, the dot product operation, and we get a parameter feed dig, which means we want to fit some value, and this is a dig, like dictionary. Do you know? Anyone know about the dictionary in Python? Yes. Okay. So this parameter means for the placeholder of t at A, we want the value of it to be A, which is the numpy array we define here. And for the B, this placeholder, we want its value to be B, also a numpy array we defined before. So basically, when you want to pass in some value to the placeholder, you either use a numpy array or you use some constant like 1, 2, 3, or a list of lists that can convert to a numpy array. So then if we run this calling, we will get the correct answer as before. Clear? This thing is also a key part of TensorFlow, the placeholder. And until now, either the placeholder or the constant, we can only evaluate their values. Constants, we just initialize the constant with the parameter we pass in, and placeholder, the value of the placeholder will be the value we pass in. The value of this node cannot change in the execution of graph. If we want to train something, the weights must change, right? If we want to train them, we want to update. Then what is the data structure we use? The name is variable. So when we say variable in TensorFlow, we just mean the data structure variable in TensorFlow. Variable is the only tensor whose value can be changed in the execution phase of the graph. So we normally use the variable to represent the parameter we want to train, we want to update. And one thing about the variable is you can also feed the value to the variable. Why this is useful? Sometimes your variable changes to a observer value, but you know what should be the correct value, but you want to verify does your graph, is your graph correct? So you can feed some value to the variables and verify that your graph is correct. And the wrong part is the variable, not your graph. So we define variable. When we define variable, we need to pass in an initial value. Like in the linear model, we define the W and C. And we also define a operation called add. You can only call these functions on the variable if you pass in a constant here, tf8, like we did this before. You will rise an error. Variable is the only thing, is only tensor that can change in the execution. So then we define two variable and operation add, print out here W and B. What we get is two variables. You see, if you are careful enough, you see there's red here. In previous one, they don't have a ref at the end. The ref means a reference. Reference means this data is mutable. You can change this data. In everything before, they will be they won't have a ref at the end, which means this tensor cannot be changed in the execution. Here. The placeholder, you cannot change the placeholder. And here we define them as variable, W and B, and they are mutable, then there will be a reference. Okay. There's also a very important thing you need to beware is here we define a variable and we pass in an initial value, but we need to explicit. We need to call the global initializer to actually initialize this variable. For constants and placeholder, we don't have to do this, but for variable, if you use, you want to evaluate the value of the variable without initializing, then you will get some very long error. Yeah, at the end, you will attempt to use uninitialized value, which means before using a variable, you need to call global variable initialized. When you call this, every variable in the global scope will be initialized to their initial value. Then we can call the run and evaluate the value of w, which is 0, 1. And here, what does this call mean? Remember how we define the add? We add 1 to this node, right? So when we call this node, it will execute the add operation. Then the value of w will be increased by 1. We call it again with 2, 3, and 4. And then if we call this one again, initialize them, then what will happen? It will come back to what? 0. To 0. So you only call this function at the very beginning. If you call this one between the training phrase, and then your variable will be initialized back to 0. To be clear until this point? Yes? Okay. And as I said before, if you want to debug, you can temporarily feed some value to the variable. Now our w has the value of 1, and we can override its value to -2. But it will just temporarily override it. If you doesn't feed it anymore, it will still be 1. Okay, all clear? And now we have 3 types of variable: constant, variable, and what's the placeholder. Then we have all we need to define our model. The second rule is to initialize variable before executing the graph. Okay, a brief summary. We use placeholder to represent the data point and label, and we use variable to represent parameters we want to train, and we use constant for other fixed value. So we can now define our SVM model. We'll use the same dataset as we used in homework 4 and see what is the performance of SVM we implement here in your homework. What is the accuracy of your SVM in the homework? Primo SVM? 80? 90? 90? First, we load the dataset, nothing thing. And then we can see our dataset have like 800 data points, and the testing set has 500 data points. Right? And we do some kind of processing for the dataset. Here we normalize them. It's not normalized, it's standardized. We will convert the dataset to a Gaussian distribution. First, we calculate the mean and the variance. Then we subtract mean and divide by the variance. Actually, we should divide by the square root of every variance here. But it doesn't change it that much. We should you will learn all this trick on the book Hands-on Machine Learning. Load it again and divide preprocessing. Okay, here we come to the key part. Define our model. First, we reset the graph previously we have already added some nodes into the graph, the default graph. But actually we don't need to do this because TensorFlow will only execute those graphs that necessary. Okay. The dimension of the dataset, or the number of features will be 4, right? 4. And we define the weight. What will be the length of the weight? 4, right? We are defining the linear model SVM will be 4. And the dimension of the bias will be 0, only a scalar. And we set the initial value of W to 40, the bias to 00. Clear? This is the only parameter we need to define. And this is the only parameter of our model, SVM. And then we can define our regularization parameter C. This parameter won't change in the training phrase, so we define it as a constant. And then this is the tricky part. We define the x, which is the data point, and y, which is the label. The shape will be num by d, which means this is a 2D array matrix, right? It will have d columns, but how many rows here? We are not decided yet. We only know it will have 2 dimensions, and the second dimension is d. This is what we call a batch of data. The batch can be like 8, 16, or 128, but we haven't decided yet. You can sometimes you can predefine the length of batch like 8. You just put an 8 here. But now, if we haven't decided yet, we just leave it as none. Everyone understand why we define like this? Okay, then we define the graph. I will write in there. In the SVM, we have 2 parts. The second part is the empirical loss, right? And how do we formulate the empirical loss? First, we do the dot product between the data point and the weight, right? And we add the bias, and we multiply them with the label. And one subtract this term, and take the max, which is maximum in TensorFlow. All right. Everyone recognize this formulation? And in our homework or in our slides, here is the summation. But I use reduce here, which is the average. Only difference between summation and average is a constant of the number of samples. Because here we don't know how many samples we will pass in here. So I use average here. And then the C here will have a different meaning. The C here will be the average constraint for each data point. In our slide, the C will be the overall, the global constraint of the whole area. So my C here will be like 800 times bigger than your than you use in your homework. Yeah, understand this point? Yeah. This is empirical loss. one is the regularization term. It's just the norm of the W. How do we calculate the norm? Multiply them together and take the sum, right? And the final loss will be the sum of these two terms. Clear? Do you have any problem here until this point? Or we are just defining our SVM model? And then, as we said before, once you define your loss, you don't need to calculate the subgradient manually. TensorFlow will do this for you. Okay, the learning rate. We need to pass in a learning rate because we want to do the learning rate decay. And the learning rate will be something we want to control for every training epoch. So we just define it as a placeholder. We can change the value of learning rate in each execution. Now here, this is the key point of the training. First, we define an optimizer, which we use the gradient descent optimizer here. What it does is exactly as we discussed in our class. It calculates the gradient and take the negative, multiply by the gradient, and add to the parameter. Nothing new, nothing fancy. And here, this operation is extremely important. Minimize the loss. It is in this function called TensorFlow calculate the gradients for you using back propagation. Minimize. Okay, that's all. We have defined our model. The next step is to training. And to train our model, as we said before, for each epoch, we randomly shuffle our data. And this is a way to shuffle the data. And for within each epoch, we want to go through the whole data set, which is we sample a batch of data and move next batch of data until we at the end of the data set. Then we go to the next epoch. We shuffle the data and go through the data set batch by batch. Here we define the predict with the, we need to specify in this training iterations what is the data point and the label we want to use. Right, just like in your stochastic gradient descent, each time you need to sample one data point and its label and calculate the gradient and do the update. And now this is the step of actual training. We define our training operation as what? As to minimize the loss, which means it will take the current batch and calculate the gradient and apply the gradient to the weight. So if we run this operation, it means we will do one step of training. Then after we do this, the weights will get updated. And we now append the loss to our history. Then we can check how does the training work. Right? And after each epoch, we do a learning rate decay. And we check the current accuracy and the training error and testing error. Then we return the history of the loss. anything? So our model will be as a linear model. The only parameter will be the regularization coefficient. Right, we take 0.5. Okay, then we define our model. And then until this line, we do the actual training. It's very quick. As you can see, basically, after the first epoch, this model converges. Then we print the training loss. So you can see after the first epoch, it already converts. So everything here will be meaningless. So that's why we have the TensorFlow. TensorFlow can let you, will let you monitor on this training curve. When you observe that it already down to a plateau, and you can end your training. You don't need to continue to train anymore. So this is our SVM model. Does anyone understand this process? Is there anything I need to explain in this process? Okay. When does this class end? Now? Okay.
Will you share that file?
Yeah, yes, of course. I will still introduce the left part of this slide. If you want to leave, we can just leave. But if you want to get a taste of how to define a neural network in Keras, you can stay and we'll finish this slide. First, we will introduce the Keras. As I said before, this is the highest level of TensorFlow, which is very convenient to use. The only disadvantage is you can only use those models that they predefine. If they don't predefine the model, you cannot use it. That's the only disadvantage. So if you want to get a taste how deep learning algorithm works, I recommend you to use Keras. Here we will demo the digit classification. We'll load this data set from the Keras, and this data set will have 60,000 of images and their label. And let's take a look at what is the content of the data set. Each image is just an image of the digits, and the label is the classification of this image. Our task is to, given this image, you predict what is this number. Right, simple. Then we also want to do some simple pre-processing of the data set. Because previously, data set is the format is integer, and it ranges from 0 to 255. But when you do deep learning, we always want the range to be within -1 to 1 or 0 to 1. So we just divide by 255. Then in Keras, doing deep learning is extremely pleasing, I should say. You just say which layer you want to use. The first layer is flatten layer, which means this, what we get is image, right? And flatten means you will flatten this whole this 2D image to a single vector. Then this image is 28 by 28. After you flatten, you will get a 700 something vector. So the first layer will be flattened. And we said the second layer we want a dense layer, which is what we introduced in our class. We just connect the input of every input of previous layer to current neuron. And since the final layer, we say we want also a dense layer, but we want 10 neurons. each neuron will correspond to one single class, one single digit. Okay, that's it. We specify which layer we want to use, and we call cares the model sequential. Sequential means this is sequential model. The data get processed layer by layer. Okay, then we define our model. And also we need to specify which optimizer we want to use, which loss we want to use, and which metric we want to use. Okay, this all the work we want to specify our model in cares. Simple enough, right? And then training. Remember how it is to train a model in primitive TensorFlow. We need to reshuffle the data and sample the best data and feed the graph and check the learning rate, all these things. But in cares, just one line. Feed. You say I want 10 epoch, and the fetch size is 128. Then you will get training. Accuracy, you can see, nearly 100. Which means we don't need some fancy convolution network to do this simple task. A densely connected network can do all this for us. Okay, after 10 epoch, you will end. We have a extremely high training error, nearly 100. And then how do we evaluate? Just evaluate. Testing error will be 98, also pretty high. And then how do we do prediction? We predict, and let's check our result. Given this picture, what will be labeled 7. And here I use the primitive TensorFlow to build the same neural network. I can see which one would you prefer? Of course, cares. But if you want to invent something new, then you need to use primitive TensorFlow. Okay, there will be the whole tutorial. If you have any question about these things, you can ask me in office hour or email me. No.
We are building by hand or
You can use the word. What is
I don't know. I was just wondering if you what? I just wondered if you know.
Yeah, you don't need to use the
Well, I'll probably try to learn it.
Okay.
Thanks very much. Your English is very good. Can I just ask you, when's the